Oh, ngala mo mutre. Hello, hello, hello. Hello, hello. Hello. Oh, kar lekhat ta mama. Yarba. A very good morning to respected invitees and everyone gathering here. On behalf of the organizers, I, Ferzam Wilina, Department of Physics, Manipur University, am extending a warm welcome to all in today's inaugural function of workshop of International Year of Quantum Science Day 2025. Now, guest of today's function, Madam Ingo Juringla, IAS Secretary, Science and Technology, Government of Manipur, and the Member Secretary, Master. Next, I would like to request on stage President of today's program, Professor N. Nimai Singh. Next, I would like to invite on stage the guest of honor, Professor A. Dilip Kumar Singh, HOD, Department of Physics, University. And last but not least, Professor Burma, Dean, Research and Development Cell, Lucknow University. Thank you. Now, let us take a moment to express our heartfelt gratitude to our esteemed guests for their valuable time. Now, I would like to request our research scholars to kindly present the welcome tokens to our dignitaries. Thank you. Now, I would like to call upon stage Dr. T.S. Gomti Devi, Department of Physics, Manipur University, to kindly deliver the welcome address.
Good morning to all. Respected Madam Kengu Zuringla, IAS, Secretary Science and Technology, Government of Manipur, and Member Secretary Mastek, Professor N. Nimai Singh, President of the Workshop on International Year of Quantum Science and Technology, and Director of the REITs, Guest of Honor Professor Muli Manohar Verma, Dean Research and Development Cell, Lucknow University, Professor Angom Dilip Kumar Singh, Head, Department of Physics, Manipur University, senior professors, faculties, invited speakers, other invitees, participants, and our MSc students, research scholars, media persons, and ladies and gentlemen. I, on behalf of the organizing committee of the REITs and MASTEC, would like to express our greatest pleasure to welcome you all to the inaugural function of the workshop on International Year of Quantum Science and Technology, celebrating the National Science Day, today 21st February 2025, held at the Department of Physics, Manipur University. Today we embark on a journey to explore the frontier of this revolutionary field where the enigmatic laws of the quantum world are harnessed to unlock groundbreaking advancement across diverse disciplines. We are also grateful to all the speakers and the participants who will lead this workshop at the best level, and we express our deep sense of gratitude to the State Bank of India, Babupara, and Mastek for their generous financial assistance in organizing this workshop. Together, let us explore the exciting potential and the transformative implications for the future. So, thank you to everyone present here in making this inaugural function and workshop a successful one. So, welcome you all. Thank you so much.
Thank you, ma'am. Now, I would like to request respected Professor Murli Manohar Verma to kindly present the keynote address.
Thank you. Honorable Secretary of Science and Technology at Manipur, the President of this conference, Professor Nimai Singh, Professor Dilip Kumarji, the HOD of the department. I'm really delighted to be here at the occasion of this celebration of the International Year for Quantum Science and Technology, which was a dream for a long time for the visionaries across the globe. And then the United Nations had decided to organize it to observe this year, 25, as the International Year for Quantum Science and Technology, to mark also the completion of 100 years after Heisenberg's paper, monumental paper, which, along with many other tenets, founded the elementary concepts behind our perception of the world. The United Nations has many objectives, so to say, to be achieved throughout this celebration, throughout this year. I am happy that Research Institute of Science and Technology in Manipur thought about it as a precursor to the National Science Day on the 28th of February. And we have a great reason to celebrate this, because we know that quantum science, it is not just quantum mechanics and technology, they are now pervading almost everywhere with the advent of artificial intelligence, quantum computing, and many buzzwords. They will soon dominate the technology. Quantum satellites being launched, And there is also a big race among the developed world, developed countries, to begin new kind of explorations based on the schemes of quantum science and technology. So several multinational companies, not without a reason, have already reached the arena. And almost 15 days ago, there was the opening ceremony at UNESCO for the International Year for Quantum Science, where big business tycoons shared the stage and they discussed various possibilities, unraveling the secrets and the mysteries behind the formation of quantum technology, and who knows how it will shape the world in years to come. The thing remains that it has been the basic quest of human mind to understand how our universe behaves, how the matter around us behaves, how light, radiation, etc. around us behaves. And in accordance with that quest for knowledge, we have tried to explore into the heart of matter. I being associated with a great center, European Center for Nuclear Research at Geneva, known as CERN, I've been associated with the center for a very long time. And then I have seen people working day in and day out, smashing all the structures inside matter, trying to see what lies inside the heart of matter. And you know what happens? When a child wants to learn how a toy works, generally, he tries to break the toy apart. To look into the heart of matter, the big accelerators in the world are doing almost the same thing, smashing the heart of matter with high energy beams, high energy protons, and things like that. So going into them is like more the energy, better will it be, or deeper you can penetrate into that structures of matter. And there is a vast zoo of the particles, that comes our way, and we are amazed at this. And also we should recall the fact that we are the humble mortals. Our knowledge has limitation. Our knowledge has limitation about the perception, about the beliefs, about the epistemology of the universe. The things nearby, could be done, could be investigated into by some means of having the big radiation or high energy particles, smashing that. Let me recall Rutherford's time, 1911. So when he just sent what they call the shells of alpha particles, very heavy particles, through very thin layered gold foil to investigate what is inside or what lies inside atom. Most of them pass through. So he concluded that atom is mostly an empty space, but some of the alpha particles also returned back. It means that there was some heavy nucleus, and most of the mass of the atom lies in the nucleus. Most of the atom is empty, the mass lying at the nucleus, like a small peanut in a big baseball stadium. So that is the size of the nucleus, having immensely large densities of 10 to the 14 gram per cc. Like, so people try to understand, what the atom is, what the particles are. Before that, J.J. Thomson had already discovered in 1897 electron as a particle. And much before that, Dalton had given the theory about atoms. Matter could be deconstructed. It could be broken into the smallest pieces called atoms. But atoms are the final indivisible pieces in the perception propagating at that time. So Dalton said no further, only up to atoms. But here we had the atoms, the nucleus, and beyond that, all these particles were not merely the particles. In 1914, there was Bohr's theory, which told us, although in a very elementary manner, like the planetary model, where the planets are moving around the sun, he thought that the electrons are moving around the nucleus more or less in the similar manner, in nearly circular orbits, and Sommerfeld modified. You see, it happens in science. The things are given initially, then they are regularly modified all the way, and there is no final frontier, so to say. Let us be very honest in saying this, that we are not the discoverer of the truths. We only discover what we perceive. We are not the scientists, or we are not pursuers of the final truths. We should not harbor any such kind of foundation. So, you see, even the Bohr's model was not correct. It was modified. Then finally, in 1923, there was this de Broglie who said that, okay, they are not particles, they are like waves. So particles were now behaving like waves. And there is a wave associated with the particles. Now, wave, the very concept means something like sound wave. I am speaking to you all, and sound is pervasive within this room, within this hall. There is no point in the hall where sound does not reach. How can a particle behave like a wave? Particle, by our concept, by our common perception, is something which is confined to a small volume, a small region of space. It should be localized. Waves, on the other hand, are like sound waves. Each one of you can hear sound. So sound is a field. If something can be perceived at most of the points, you call it field. You don't call it particle. Particle is confined, like all of you sitting in your own chairs. But sound is a wave. So I'm talking to you, and each one of you can feel that. Means there is some intensity of the sound energy which is present there, and your ears are the detectors. They can detect it. How can the particle be a wave? How can the particle be present at various points at the same time? So there were, I will say, several gentlemen. I should not name only one or two. I should not name only Heisenberg or Schrödinger or this or that. You see, the theories or scientific edifice is built by the great toil, hard work of many innumerable persons, although we can name a few for the sake of convenience. So it was called a wave function. Now, wave function is a field. The particle has to be a field. There is no particle, but only fields. There is no electron, but only a field of electrons, described by something, and that something was called at that time as psi function. Schrödinger was one fellow who gave a mathematical expression how this psi function could propagate, how this could evolve with time. But then there is always a possibility of finding that particle in certain place. It was a fantastic business, very enigmatic, so to say, that the particle is losing its essence in being confined to a place. On the other hand, it is being described by a field. It could be present anywhere. You don't know about its presence. You can only predict the possibilities. It can be here or there or there or there. This is the probability of finding that particle here, like this and that and that and that. It is all like a smoke in the air. It's not like a particle. It's like a smoke in the air. You can only say that the probability of finding that particle is at this location is this much. At another location is that much. So describing everything in words of what you call probabilities. So it's all a probabilistic world. And it was against our common perception where we are accustomed to think in terms of determinate things. You must tell me whether it is here or not. It could be 0 and 1. Either it is here or it is not. Either a cat is dead or alive. It cannot be in the superposed state. It's looking like a hocus pocus. The same Schrodinger who described the world in the terms of probabilities, 10 years down the line in 1935, he designed one experiment called Schrodinger cat paradox, a Gedanken experiment, thoughtful experiment. It could not be realized in practice. It is very interesting to talk about it, even in the common parlance, because it is one of the objectives of the United Nations also to convey the spirit of quantum science and technology to common man. It should not be a discussion merely for the academicians, although the things involved are really very, 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 very crazy. They are so crazy that they are shaking the very foundations of your deterministic understanding. They pervade across philosophy, science, art, literature, you name it and you have it. And that is the reason why everyone should be made aware of quantum logic. So I was telling you, it could be here or not here. The cat in a box could be either dead or alive. But here was this great experiment known as Schrodinger cat paradox experiment. Here is a setup. Let me take some time to explain it to you in a simple language, although I don't have slides to show. Imagine there is a big box and you leave a cat, a poor cat, inside that. The cat is alive. And then you think of a very deadly contraption. You think of a device, some radioactive material. You know, radioactive materials have the probabilities of emitting the particles, which we know as alpha particle, beta particle, gamma particles. So suppose you have some kind of radioactive material inside the box that will emit a particle sooner or later. You don't know when. Suppose that particle is emitted and there is a hanger. Through that hanger is suspended a hammer. The hammer will fall on a glass jar. The jar contains cyanide, a toxic, poisonous material, hydrocyanic acid or something. The hammer falls on the jar breaks apart, the hydrocyanic acid, the poisonous material flows outside, up to the poor cat, and the cat, by eating it, immediately dies. Think of this, the series of setup. So you have the radioactive material, the particle is emitted, you don't know when it will be emitted, you are never certain about it. That is the nature of radioactive materials. The particle, if emitted, will allow the hammer to fall down, to break the jar, to allow the hydrocyanic acid, which is the toxic poison, to flow and to kill the poor cat. So this is the idea behind this kind of a box. Now suppose the box is closed. You close the lid and then you stand outside. You have no way to see through that. You wait, let us say 1 hour, and there is a 50-50 chance of the particle being emitted by that radioactive material which I just described. So 50% there might have this ejection of the particle, emission of the particle, and the cat might have got dead because of the following processes. And there is 50% possibility of no emission at all. In that case, nothing wrong will happen to the cat and the cat will stay alive and happy. 50-50% chance. I am the observer who is standing outside the box. I have not opened the box. I am only waiting. What is the fate of the cat? Whether the cat inside is alive or dead. I wait long enough. 1 hour, let us say. But I am not sure. It might have been dead, it might have been alive. How does the quantum mechanics or quantum principles, how do they describe such kind of situation? They say the cat is in the state of superposition of life and death. That means If there is a 50% chance of it being dead and 50% chance of being alive, then all I can say is it is half dead and half alive. Until and unless I open the box and see for myself, good luck, the cat is alive. But before I open the box, until I open the box, the cat is in the superposed state of being live, alive, and dead. It was not admissible to Schrodinger, who the ideas which actually ran through all the probabilities, and they were more or less established. Suddenly there was a shock to Schrodinger's mind that something is wrong somewhere. The cat cannot be dead and alive at the same time. It has to be either dead or alive. How do we know it? Unless we open the box. The very act of measurement tells you the reality. Unless you conduct the measurement, you won't be able to find out whether the cat is dead or the cat is alive. Here is the role of the observer. The observer is making the observation, is making a measurement. Only at the time of measurement, you know the answer. It is like someone, you are sitting in your home, someone rings the bell, call bell, doorbell, and you open the door. Until you open the door, you will not know who may be outside. Only at the time of opening the door, you shall be able to find out the information who's standing outside. Believe it or not, it's true that the world opens its reality to you only at the time of your observation. That observation is cut to a point, cut to a time, cut to a moment, cut to a epoch. Not before that. Then here was the puzzle with Einstein. You see, if you find a particle here, you conduct the measurement, you find it here. The question is, where was the particle just before the measurement was done? Just before that. Now, in philosophy, people who are called realists, they will argue it was there. The particle was there at the same location, even before the act of measurement was done. If it was there, quantum mechanics is not able to tell you where it was. It means quantum mechanics is incomplete. Even though it may be correct, in giving you the probability of finding the particle at a particular location, since it is not able to tell you where the particle was before the measurement was actually done, before the lid of the cat box, Schrodinger cat box was open, you could not find out that. So before the measurement was done, you are not able to tell where the particle is, and therefore Albert Einstein said, we knew that the particle was there, but your theory is not able to tell us where the particle was. So your theory is incomplete. So this was a debate at that time between great minds of the world. In science always progresses with debates. Let us try to understand it time and again. Let us remind ourselves there are no final frontiers. There are no final truths. It always propagates with debates. It is all ad hoc. We only have to enjoy the journey of doing the research. So, realist would say that particle was there, but your theory is incomplete, quantum mechanics is completely incomplete, and Albert Einstein's EPR paradox, Einstein, Podolsky, and Rosen, EPR paper had been very monumental, published in 1935, which had fallen into debate with these basic principles of quantum mechanics based on uncertainty given by Heisenberg. You all know uncertainties means there are uncertainties with the world. You are never deterministic. You would never know where the things are until you do the measurement. When you do the measurement, when you open the box of the cat, You call it collapse of the wave function. Before that, there were possibilities. But now when you open the box, you conduct the measurement, you find the cat is dead or cat is alive, the wave function collapses to one single probability, which is your truth. So you say, cat is alive. You declare you are happy at that moment, cat is alive. Or you are sad at the moment when you realize the cat is dead. But this reality is only opened out at the time of opening the box, and this is called in technical parallels collapse of the wave function. Until and unless you do that, everything is just possibility. So the second orthodox view was the particle was there, but we did not know about it. That's the common sense, common perception of well known as the Copenhagen interpretation. You all have the probabilities described by that psi function, which was the field, as I told you with the sound example. And that psi function could only give you some probability of finding the particle in certain region. There could be a third view also made of agnostics. Agnostics, you know, are the people who are not ready to believe the things because they do not know. They always claim we don't know. So they would say they refuse to answer the question where the particle was before the measurement was conducted. They said it carries no sense because we can't have any information before we conduct the measurement, actually try to interact with the system. You see, when you interact with the system, you kill the originality of the system. And you don't recognize the system as it is. What we call as the pure states. There are no pure states possible. Purity is possible only until you don't interact, until you interact with that. So before interaction, it could be pure, but as and when you try to interact with nature, suddenly it knows about your intentions, it changes its course. And it has been beautifully explained by various well-established experiments, like double slit interference experiment, very celebrated experiments. For the sake of simplicity, I will not go into all those details. But if you like to know whether the particle, a particular entity is a particle or a wave, the enigmatic thing is nature does not tell you a straightforward answer. Nature it doesn't behove me to answer the question. If you ask me whether electron is a particle or a wave, whether light is wave or particle, it could be both ways. And the idea behind this is that unless and until if you conduct the experiment, nature knows beforehand your intentions and it shows only that side in which you are interested. So to say, if you want to observe the nature or a particular entity as particle, and you make your experiment specially designed for observing it as a particle, it will show only that side to you and it will declare, okay, this is the particle. And if you design your experiment not to find, not to delve, not to investigate, not to inquire whether it is a particle or a wave, just leave it open, it will behave as a wave. So the interference would be caused. Interference, the property through which we can establish that it is a wave. Even the single photon can interact with itself to create the interference. So the single photon, which you call as particle, has the wave feature because it can interfere with itself. And interference is a short sign of the wave characteristic. So it's called complementarity again. Complementarity means either this or that. It couldn't be the both things at the same time. So in Hindi they say, you must, I don't know whether I can speak in Hindi, a few couplets. Kabir, you must have heard about Kabir, right? Jab main tha, tab hari nahi. Jab main tha, tab hari nahi. When there was I, there was no God. Ab hari hai, main nahi. And now there is God, but there is no I. So they are, in technical language, they are called canonically conjugate variables, like position and momentum. If you can determine position with certainty, and you say, look here, particle is here, this is the position of the particle. You lose all information about the momentum of the particle. So you have to make a trade-off between your information. You cannot have all the good things in your favor. Either you can have information, precise information about the position, or you can have information about the momentum. Similarly, you can have different pairs of the quantities in physics. It is not complete. The wave function collapses only when you try to observe it. So there was a debate going on between the realists who said that quantum mechanics is incomplete theory because it doesn't tell you where the particle was before the observation or experiment was conducted, measurement was conducted. People actually went into the extent of saying that we are the outcomes of our observations. We produce what we desire. We observe what we plan. Because we are planning something as a particle, it will behave as a particle. People said we are participating in producing our results. There was Wheeler, a very celebrated scientist, John Wheeler, who was thinking like that. So in 1964, there was John Bell. Most of you may have heard about John Bell. He was a young scientist. And he designed a very thoughtful but complicated kind of an experiment to decide whether who is the victor, who is finally victorious in this tug of war between quantum mechanics with a set of principles which were difficult to understand, which were completely doubtful, which were completely confusing. And on one hand, on the other, deterministic theories which say things should be determined, they are not probabilistic. You can find the answer in black and white. Either it is there or not there. It cannot be both ways. Either you are dead or you are alive. You cannot be both dead and alive at the same time. Law of the excluded middle. So 0 and 1, black and white, is the realistic argument. But 0, 1 and any combination of 0 and 1 is quantum mechanical argument. And based on this argument is the computer, a new kind of logic, quantum logic. Because normally our classical computers that we hold on our tabletops, they work on the Aristotelian logic, Boolean algebra, 0 or 1. It could be false or true. But qubits, the quantum mechanical computer, they work on binary logic, but they work on the qubits. Qubits are 0, 1 and any possibility or any combination of 0 and 1. So it will explore all the possibilities at the same time. This is the main idea behind the technology which is known as quantum computing technology. The entire logic is different. Our understanding is thinking in terms of 0 and 1 only, black and white, this or that, life and death. Can we ever perceive a human being to be a combination of being dead and alive at the same time? That bedazzles our perception of life and death. Because of the simple reason that we human beings are accustomed to understand the world in the classical framework. Although we ourselves are the byproducts of the quantum phenomena. And who knows, we are not big enough to be called as classical objects. We could also be quantum objects. Being small and large is always in comparison. In view of the whole universe, which is 3000 megaparsecs large, the visible part of the universe is 10 to the 27 centimeter. So that is the size of our universe. We are a tiny specks. We are tiny dot, quantum dot, so to say. We are not big enough. We should not have any kind of attitude. Science will teach you that kind of humility. It will teach you that kind of humility to believe in the basic tenets of your understanding, and that is what comes your way. It doesn't lead you to the ultimate reality. There is no ultimate reality. Quantum mechanics makes it clear once and for all. Can we have your attention, please? The two ladies there. Thank you. So, the reality comes your way. You have only your viewpoints. I'm looking at you from my viewpoint. You are looking at my face from your viewpoint. That is your reality. And my bit of reality comes from my understanding. We are all buckets. We are evolving. Human beings are evolving. We do not know the final truths. We are not big enough. We are not mature enough. 1 lakh years before, we were not in this position. 1 lakh years down the line, who knows where we shall be. Our understanding, faculty of understanding, is totally governed. If I ask you how old you are, you will tell me so many years, but that is always from a reference line. But believe it, you are one with the universe. The particles in your body came with the universe, and they evolve with the universe. So our universe, right now, the current wisdom goes, although it may not be quite correct, starting from the Big Bang, it has age of 13.7 billion years. That should be the age of each one of us. So we are contemporaries without any kind of fluctuations. Of course, the microscopic changes are there, statistical fluctuations are there, but then we are evolving along the arrow of time, in which the entropy is increasing and all that. I was talking in 1964, there was this gentleman, John Bell. He designed one experiment to settle the question once and for all, whether who is the winner, the quantum mechanics or the realist theories. The realist who said the quantum mechanics is incomplete, and because it is incomplete, there must be some hidden variables because our ignorance does not take into account all those hidden variables. There should be some more parameters to be included into it so as to make it more complete. So that is called a hidden variable theory. Who is the winner, Einstein or Bohr? And that was a great debate even in 1927 when there was a big Solvay conference. I think people from physics must be knowing about it. In Solvay conference in Brussels in 1927, there were 29 great illuminating minds of that time, scientists who tried to settle the score. Who is the winner, quantum mechanics or EPR, Einstein's theory of deterministic world? In philosophy, it is called ontic reality, ontic, and epistemology. Epistemology is the knowledge that I acquire, which is my piece of my side of truth. It may or may not be correct. But epistemology is the acquisition of knowledge on my behalf. Ontology is something which is existing in an objective world as an objective reality, independent of the observer. That is why there is a famous question, interesting question, Einstein, Alexander Pius mentions in that book, God Doesn't Play Dice also. Einstein went outside on a stroll and he suddenly asked his biographer, looking at the moon, do you believe that there is no moon when I'm not looking at it? What will be your take? You will definitely say, yes, there is a moon, even when you are not looking at it. This is what Einstein thought. Quantum mechanics says, no, we don't know. Then Einstein reverts. You don't know because you are incomplete. That is what, mostly Einstein was not against quantum mechanics towards the end of his life. He believed in quantum, but he still maintained that quantum mechanics is incomplete theory. There are hidden variables which are not known to us as human beings because of maybe our own limitations. Our faculty of understanding is also evolving with time. Maybe 1 lakh years down the line, we shall be more educated, more intellected people. And just as in the primitive times, we were fruit pickers in the jungles, the primitive human beings, like Neanderthals or other species, right? We were not Homo sapiens in the same way. Our mind is evolving. So Einstein said you are incomplete theory. And then Bell's inequality decided that no, quantum mechanics is correct. There were several versions of the Bell's inequality later. Various experiments were designed using photons. I will not go into those details. They are complicated but equally interesting because they were designed to settle the answers, to provide the answers among this great confusion and conflict between quantum mechanics on one side and the deterministic science on the other. So is also given to Zeilinger and Clauser, three gentlemen who conducted the experiment to verify the Bell's inequality. Bell's inequality was equality, then quantum mechanics will win. Otherwise, the other side will win. And now the things have reached a state where we have reposed our faith in quantum mechanics, and we think that everything based on the science is correct. And here is the technology also coming out of that. So quantum science and technology. Technology cannot come out of nothing. There have to be very solid scientific principles behind that. It is not deterministic, it is all probabilistic, but still it is deterministic in some sense. Can you get that point? It is called unitarity. Unitarity. You know there are probabilities, but you know how the probabilities are evolving with time. So at least in that part you are determined. You have that determination. Like you have the smoke of in the room somewhere, plume of smoke. So you don't know where the things are, but you know how the smoke is evolving. After some time, the smoke which is like this will grow to that size. And on. Schrodinger equation tells us this. Precisely the evolution of the field related with electrons. Roger Penrose, in his famous book, I would urge everyone to read that book, Emperor's New Mind by Roger Penrose. He describes this phenomena and calls it unitarity. Unitarity in quantum mechanics. That things are probabilistic, but you know how the probabilities are evolving. And there you are sure of that evolution. So it is unitarity. But then it is sometimes when you observe something, you get one result. Before observation, you can just keep conjecturing. There could be millions and millions of results, all in the Hilbert space. Just like after death, if a human being dies, where he or she goes, keep wondering. He or she may have been lost in some world. We human beings are not able to make any conclusions about that. And then there are possibilities in Hilbert space. And I should talk about, at this point, an interesting concept known as many world interpretation. Many world interpretation. There could be billions of probabilities until you conduct the measurement and you know about it. Those billions of probabilities still are not cut to a point. They appear in different worlds. The cat could be alive and dead. In your world, it is dead. When you open the box, in the other world, it could be alive. But the two worlds do not interact with each other. This is the basic idea behind many world interpretations. You can have large number, you can have a billion possibilities, billion probabilities. You don't know. Each probability corresponds to one single world, or so to say, one single universe. But those different worlds are not interacting with each other. Therefore, there is no exchange of information between them. So when you open the box, Schrodinger cat box, you find the cat smilingly coming out. You say, it is alive. And then, believe it or not, in the other world, the cat must be dead. So there have been different states, each state in its own world. But there is no interaction between those worlds. Therefore, there is no contradiction. This interesting idea was given by an intelligent scientist known as Everett in 1955. Everett's many world interpretation. So people have said now things are boiled down to a state where we say that we do not understand many things. It is still very confusing. Observer is the part of the observations. You produce your results which you desire. Nature knows about your intentions. Nature is not away from you. You are entangled with the nature. In so much so that they are not separate at all. Because this was also a famous point of debate between Einstein and Bohr. You see something like this. You know, there are two electrons and they cannot retain the same state of spin. So one is up, the other one is down. And if you keep them away, take them away, like say 1,000 light years away, and you suddenly try to look at one electron and keep the spin down, this electron will immediately have the spin up. Because that Pauli's exclusion principle has to be obeyed. That is a secret, sacrosanct tenet of quantum mechanics. Einstein wondered it could not happen. Because how could the influence from one electron travel all the way to another electron, which is 1,000 light years away? Even the light will take 1,000 years to propagate from one point to another. How could that effect transfer or propagate instantly? If something happens instantly, we call it non-local. And therefore, quantum mechanics is a non-local theory. Einstein disbelieved in this. He said, no, things should be locally influenced. A signal has to be transmitted from one point to another. At most, it can be fastest at the speed of light. Quantum mechanics answers this question as the following. It says that two particles are entangled right from the beginning. They are a single system. There is no transmission of the signal from one electron to another electron, ordering you keep your spin up because I have my spin down. And then this spin up, immediately that one down. There is no transmission of information between this. It is instant. To Einstein, it is not acceptable because Einstein believed in a local theory. But quantum mechanics is a non-local theory. The things are entangled. There is an entanglement, not only between those atoms, but also with the observer. It means that human consciousness somehow enters this business. Because the ultimate decision-making power resides with the human brain. It is deciding that. And that is why people are now talking about quantum consciousness. I would warn you against some pseudoscientific claims about quantum world, because many people, knowingly or unknowingly, just propagate the things in the name of quantum mechanics, and they try to mislead public in a way. Quantum meditation. There have been a number of variations of this, and we have to be cautious about this. Things have to be ultimately understood in scientific language. So my take is that it is something like this entanglement is something like a famous example. I'm tempted to give that. See, Bertelsmann socks. If you Google this, Bertelsmann socks. So, there was one gentleman named as hypothetical, one gentleman named as Mr. Bertelsmann, who was a very strange kind of person, a philosopher, who wore two socks in the feet, and if one sock was of a pink color, the other one was not of the pink color. Okay, so different colors, or let us say red and blue. So if one sock was red, the other one could be blue, other one could be some other color, right? But not red. So if you could observe only one sock, you could get the conclusion about the color of the sock in the other foot. It does not necessarily mean that there is some information which is traveling from one sock to other sock. Okay? It is only about the character of Mr. Bertelsmann, because you are aware that he is a very eccentric guy. He is wearing a red color sock in the one foot, so you only observe that foot, and you find it is red color, immediately get the information that the color of the sock in the other foot could not be red. How did you get this information? About the other foot that could be long apart, long way off. Has some information propagated from one foot to another? No. It is the very nature of Mr. Bertelsmann, who is eccentric by his psychological traits. He does this kind of a strange activity. Nature, who knows, could be like this. There could be a single mind in the whole universe. And there is no propagation of signals from one place to another. All entangled, the system as well as the observer. And there is a kind of a U. You can imagine this U, the different branches, going to the early universe, we all had different branches. We were evolving like the branches of the trees. And we, human beings, came from DNAs or all that, accumulating mass, accumulating consciousness. We became the human beings. The other guys there became birds or insects or leaves or some other kind of things. And you are observing that now. Even the particles, electrons, protons, neutrons, they had the life of their own. And you are observing from one vantage point. You could not claim that you are the only conscious human being in the world and the rest, poor guys, are all material objects. Because you have been, in the flashback, run the story back, you were the part of the system. You were all the same. The universe did not come out of nothing. It came from a single. It's smaller, it's smaller. We all know the universe is expanding at a tremendously fast rate today. It is an accelerating universe. So by reason, it must have been shorter and shorter and shorter and shorter in the past. You were all together. There were no birds, no insects, no human beings, no DNAs, no molecules. Okay? Initially, there were all radiation. Even before that, there were only field. We are trying to delve into those questions when we think about the quantum universe, quantum world. Who knows the answer? But these are the frontier questions that we are facing today. Thank you very much for giving your kind attention. I thank the organizers also for giving me this opportunity to present my talks. Thank you very much.
Thank you, sir, for sharing a detailed introduction to quantum science and technology. Next, I would like to invite respected Professor A. Dilip Kumar Singh to kindly present.
Sorry. A very good morning to one and all. Respected Madam Kengu Zuringla, Secretary, Department of Science and Technology, Manipur, Government of Manipur. Professor M.M. Verma, guest of honor, and today's President, Professor Nimai Singh, and all those who are present here. I welcome you all to this. And so the workshop is about the International Year of the Quantum. And this year marks the 100 years of the development of quantum mechanics as it was done by Heisenberg on an island. It's 100 years. And this era, as of today, also marks some important developments. And those developments are related to what we are commonly now hearing, that is artificial intelligence and quantum computers. The year 1997 was a landmark year, and in that year, the computers, for the first time, defeated a reigning world champion in chess. That was in 1997. The next development in AI happened in 2016, when the AlphaGo defeated the reigning world champion in Go, a game that was invented and which is played mainly in Japan, but which is now played by many other people from different worlds. Now, defeating a human Go player was considered to be a landmark or the last barrier that an artificial intelligence could defeat in terms of the games that is played by humans and that is based on our mental capabilities. So that was in 2016. Now, in the other aspect, the quantum computers are believed to be another technological milestone, and the quantum computers for the first time in 2019 achieved what is called as quantum supremacy. Quantum supremacy indicates or is a what do you say is a measure in which a quantum computer can perform much better than a classical computer. In the 2019, this was achieved by a quantum computer that was built by Google. It had 53 qubits, and if you think of qubits as just 0 and 1, and if you look at the state space that is spanned by the 53 qubit quantum computer, it is like 2 to the power 53. And 2 to the power 53 is equivalent to 10 to the power 16. Now that is a kind of a quantum system, and if we are to calculate the kind of a state such a system can have in terms of the classical computers, it is believed that it will take at least 10,000 years. However, the quantum computer with 53 qubits achieved it in just a fraction of a second. So what I'm trying to emphasize is that we live in an era that could perhaps in future be remarkable in terms of the turmoil that we face today. There is war everywhere on this every corner of the world, but at the same time, we as a human race also face the daring or the what to say a terrible or a terrifying future that is imposed on us by the global warming. But along with it, we also have these two technologies that have developed in the recent past. And that's going to define how the trajectory of human civilization is going to be in the next few centuries, perhaps. And those two are the artificial intelligence and the quantum computers. Now, the artificial intelligence, as we have read in recent times, can be achieved with a very economical use of computers that was demonstrated by the Chinese company DeepSeek. So what we're going to see perhaps in the future is a convergence of technologies. The way how we look at AI is now using classical computers. Is it also possible that in the future the AI that as we know of it will also use or will take advantage of the quantum supremacy? At the same time, what we are seeing is that a development in terms of the machines being able to think and think better than us in terms of the AI, and at the same time, a quantum device or a quantum revolution that's happening on the instruments and on the devices that we use. So we see these two parallel developments, which are really remarkable, and that's happening in our times. And perhaps if we can take advantage of the quantum mechanics, if we can take and if we can reach out to people to let there be a popular understanding of quantum mechanics, perhaps we are paving the way for how the technology will develop and will be used by the common people in the future. So in that respect, organizing this kind of a workshop is perhaps the way to do that. And I should thank Professor Nimai for doing this. I think we have achieved at least a small milestone by having and by organizing this kind of a workshop. And perhaps in the future, we'll see these convergence of technologies. And perhaps for those of you who are attending this workshop, you'll remember that, yes, this was the first event as a part of the celebration of International Year of the Quantum Science that you attended in the Department of Physics. And maybe another decade, 2 decades, 3 decades down the line, those of you who are in PZ will see how quantum mechanics is going to evolve and is going to affect our life as we live in day to day. Thank you all. Enjoy it.
Thank you, sir, for sharing the drastic development of quantum science and technology. Now, may I have the pleasure to invite Madam Kengu Zuringla to kindly deliver a few words.
Good morning, everyone, all gathered here. Today, we observe a workshop on International Year of Quantum Science and Technology. which is being jointly organized by the Research Institute of Science and Technology and Manipur Science and Technology Council. I am privileged to be a part of this workshop. My deep respect to the President, Professor N. Nimai Singh, the President of this workshop, the guests of honor, Professor A. Dilip Kumar Singh, the Head, Department of Physics, Manipur University, and Professor Murli Manohar Verma, the Dean, Research and Development Cell, Lucknow University, esteemed academicians here, the professors and students, and the organizers. We understand that this quantum science and technology has impacted our society in all spheres of our lives. We understand that this quantum science and technology will still impact our society to a great extent in the field of science, in the field of medicine, in the fields of education, in fields of mitigation of environmental disasters. It is with great concern that I urge our young minds, the scientists and the innovators, as you continue to research, as you continue to pursue on this knowledge, we urge you to use your knowledge to bring greater development for our society. We urge you to use your knowledge to bring better medical facilities to our societies. We urge you to use your knowledge to bring a better life to our society, to alleviate pain, to also see how we can bring about a better standard of living in our society. And therefore, as we hold this workshop and as you study minutely into the quantum of science and technology, we encourage you to study deeper. We encourage you to look into things which human eyes cannot see, which will definitely impact our society to a better society. And you are the one who will be the game changer. You will be the one who will bring about a positive change in our society through the knowledge that you gain and by utilizing this knowledge that you have gained for a better society. It is also my wish that you will make the best use of this workshop for these 2 more days that we will have, and that this also will benefit each one of you greatly. Thank you.
Thank you, ma'am, for your speech. Next, I would like to request Professor N. Nimai Singh to kindly share a few words.
Respected chief guests of today's function, Madam Kengu Juringla, IS Secretary, Science and Technology, Government of Manipur, and a Member Secretary, MASTEC. Professor A. Dilip Kumar Singh, Head of the Department of Physics, Manipur University, and Secretary of this workshop. And Professor Murli Manohar Verma, Dean Research and Development Center, Lucknow University, who is the keynote speaker of this workshop. Respected invitees, Professor Amuba Singh Sir, Professor Jakin Sir, our R.K. Dilip, brother R.K. Dilip, Professor Rajmohan, and Oza Subhas, and many others, Oza Damanti, and Oza Samu, many others participant, all college professors and teachers, research scholars and students. I want to congratulate, thank Professor Murali Manohar Verma because whatever I wish to speak, he had already spoken. So my job is now reduced. But one point, I want to give a small remark, and he won't mind that John Baird, the Irish physicist, he published his paper in Physics 1, 1964. It was a mathematical inequality. He read the EPR paper very well, and from there, he found something new. So he derived an inequality, a correlation inequality. If it is below that one, Einstein is correct. If it is above that one, Bohr Copenhagen interpretation is correct, that inequality. When this inequality was seen by Alan Speck and many people, so they feel that, oh, it can be tested by experiment. That was thing. And these three people, that is the thing I want to mention. So on 4th February 2025 in Paris, at the headquarters of the UNESCO, this International Year of Quantum Science and Technology was launched. And in that function, Nobel Prize winning physicist William Phillips remarked, "It is not that there is nothing deeply wrong with quantum mechanics. It is that there is something deeply wrong with your ability to understand it. The mistake is not quantum mechanics, the mistake is ours because we cannot understand fully. That is the thing. So with this hope, we should pursue the matter. First, everyone has spoken that this function, these international years of quantum science and technology has a few primary goals. Number one, to increase public awareness about the importance and the impact of quantum science and technology to the masses, not to the scientists only, to the children, to the family members, everyone, okay, to the masses, common people. That is one message. In Europe and America, the quantum mechanics subject and quantum science has been introduced in high school also. How they should introduce, they have planned. That is number one. Another is, we are old people, we will die after a few years, old people. We have to build, we have to train young people. So in that way, to inspire the next generation of scientists and innovators by highlighting the potential of quantum science to address the critical societal challenges. So this is also called capacity building in another term. That is number one. We want to nurture the future scientists who can contribute in this quantum science. That is one aim. Another is to promote the global collaboration among the scientists, educators, and a policy maker to advance quantum research and application. I cannot do alone here. I have to have collaboration with America, with other countries, with many other advanced countries. So it is overall, it is not a one-man job. It is nowadays research institute, research work, thousands of people together working in CERN. Our sir must be knowing better than me. So collaboration is important. And we need collaboration from policymaker. Finally, it should be done by policymaker, not by us. Okay. Without money, we cannot work. Without planning, we cannot work. So finally, policymaker. So this is why in America, when Donald Trump came up, scientists are very they're worried. Okay, that is the point. So as I told you, we have to support education development to prepare for quantum revolution, starting from high school curriculum. And these organization, these function can be organized by individual also, by school also, by institute also, okay, by higher institute, government agencies also. It is not confined to research institute to organize this function. Okay. So in one way, it is to support the United Nations Sustainable Development Goal, in short, SDGs. Okay. That is the thing, and created the problem. It was problem how to interpret the wave function. So it was born, and many other scientists later on interpreted the wave function. Square the wave function is the probability density to to measure the particle's existence at that point. So things became undeterministic. So Einstein remarked that the famous phrase, God does not play dice with the universe. Einstein believed that everything should be deterministic. Localism will come later on. So the problem in quantum mechanics, not the problem, the property in quantum mechanics is the superposition principle, is our professor told that zero, not 0 or 1 can be superimposed. Life and death can be superimposed. Two wave function, they will be superimposed. Superimposed principle is one concept which is not in classical mechanics. Another concept is called measurement. As I told that, only when we measure we will declare that a particle exists. That the moon, he gave the example of moon. Superposition principle, measurement theory, okay. Then entanglement will come. Non-locality, realism will be violated, localism will be violated. All these things will come. Finally, the Solvay Conference of 1927. It is the clash of titans. Here, Bohr one side, Bohr, Heisenberg, Pauli, many people on one side. They are following behind Bohr. And Einstein, Schrödinger, and these people on one side. Einstein and Bohr, they will argue in the Solvay Conference. Einstein will propose one, Bohr will defeat. Next day again, Einstein will come with some other argument. Next day, Bohr will defeat. So in that way, virtually Bohr won the game in that debate. But Einstein was not happy. So what happened after some, in the textbook, we started learning the Copenhagen interpretation. Copenhagen is the place where Bohr was there. So this is why it is called Copenhagen interpretation. Okay. Bohr Institute was there, so all people visited near Bohr. Heisenberg used to visit to Bohr, so this is why Copenhagen interpretation. But Einstein was not happy with this thing still. So he, along with two his juniors, number one, Boris Podolsky and Nathan Rosen, two young people. He called two young people and wrote a paper called Einstein-Podolsky-Rosen paper, in short EPR paper. So in 1935, our professor told, in EPR paper, Einstein put all his effort to argue that he's right. quantum mechanics is not complete until and unless there is something. Spooky action, hidden variables, something should be there. Otherwise, quantum mechanics is not correct. So that paper could not be defeated by anybody. There is no leakage, argumentation, everything is fine. The paper is with me also. So nobody can defeat that paper. If you read the paper is correct. So Bohr will be wrong. But somehow, after some year, in 1964, after many years, Irish scientists, Ireland is famous for many good people. Okay. James Bond also maybe. Anyway, Irish people, John Bell, he was a scientist at CERN at the time. So John Bell read EPR papers again and again, and he discovered something new in that paper that I told you. Okay. If hidden variable is needed in Einstein's argument, then one thing, if Copenhagen interpretation is correct, one thing, so he formulated as an inequality equation in that paper. And that was, and below that inequality, Einstein would be correct. Above the equality correlation, Bohr would be correct. So this is Alan Speck found one opportunity. He is not believing either Bohr or Einstein. He was an independent person. He claimed that his style of learning physics is that he don't believe anything. He believe himself, and he want to test the thing. So that is why he jumped upon. He visited to the Bell that I want to test your inequality. Bell thought, don't go into this field, you will be mad. So, but anyway, he decided to do, and he performed the experiment from France, and other two people also independently performed. This is why they got it, and entanglement was correct, and the Copenhagen interpretation is correct. There is no need for hidden variable. There is no need for spooky action. Non-local is the character of quantum mechanics. Superposition is the character of quantum mechanics. Measurement theory that only when we measure, the particle exists. Only when we see the moon exists. Otherwise, moon may not be there. So that is correct. So this is what. An outcome of this thing is that, as he told, that signal goes instantaneously. And it violates the causality, Einstein's special theory of relativity, general theory of relativity. Things are very serious again. So this is why the outcome of this entanglement is the quantum computer. So now quantum computer is in action now. And the worry is that okay, the research director from government of Ghana in inauguration of this international year, let us commit to making quantum science accessible to all, to make an equitable and a prosperous future for all, because he believed that it will be only for America, it will be really only for European countries, Chinese country. We poor people in their like obscure places, we cannot have any access. So there will be digital divide. How to stop the digital divide? That is his worry. So I am the organizers. I should respect the timing, and I think I will stop here. Thank you very much.
Thank you, sir, for informing us the importance of today's workshop and as well as for sharing the early development of quantum science. So, to conclude today's function, I would like to invite on stage Dr. A. Kesorjit Singh, JM University, to present the Board of Thanks. And after the Board of Thanks, I would like to request everyone to have light refreshment just outside this conference center.
Respected Chief Guest, President of the workshop, guests of honor, distinguished speakers, faculty members, students, and esteemed guests. It is an honor to deliver the vote of thanks on behalf of the Research Institute of Science and Technology, Imphal, and Manipur Science and Technology Council for the inaugural function of the workshop on the International Year of Quantum Science and Technology at the Department of Physics, Manipur University. At the outset, I express my heartfelt gratitude to our chief guest, Madam Kengu Juringla, IAS Secretary, Science and Technology, Government of Manipur, and Member Secretary, MASTEC, for her encouraging words. Her presence, along with the scientists and staff from MASTEC, today highlights the significance of promoting academic and scientific research and education in our state. I extend my sincere thanks to the President of the workshop, Professor Nimai Singh, for his unwavering support and leadership in organizing this event and bringing together such a distinguished gathering of scholars and researchers. A special appreciation to our guest of honor, Professor A. Dilip Kumar Singh, Head Department of Physics, Manipur University, and Professor Murli Manohar Verma, Dean, Research and Development Cell, Lucknow University, for their insightful remarks and encouragement to all the participants. A big thank you to Dr. T.S. Gomti Devi for delivering a warm and heartfelt welcome address that set the tone for this workshop. Our deepest appreciation again goes to Professor M.M. Verma for delivering an enlightening keynote address, setting the stage for the discussion that will follow over the next 2 days. His expertise and perspectives have provided us with a strong foundation to delve into the depths of quantum science and technology. I also take this opportunity to express gratitude to all our distinguished speakers and resource persons who will be engaging us in thought-provoking sessions over the next 2 days. Your presence and willingness to share your expertise are invaluable to this workshop. A special mention to the Scientific Organizing Committee for their tireless efforts in meticulously planning and executing this event. To all the invitees, participants, thank you for your enthusiasm and keen interest in quantum science. Your active engagement will undoubtedly make this workshop a meaningful learning. Manipur University for their excellent support in hosting this workshop and ensuring all necessary arrangements. Our sincere gratitude to the print and electronic media for covering this workshop. Finally, I'd like to thank MASTEC and the State Bank of India for their sponsorship and continuous encouragement in promoting scientific research in the state. Their support has been instrumental in making this event possible. With this, we officially conclude the inaugural function, and I invite you all to join us for a light refreshment before we proceed with the first session of the workshop. We shall reconvene after 5 minutes. Thank you once again, and I wish everyone a fruitful and engaging workshop ahead. Thank you.
Research Institute of Science and Technology compiled the biography and autobiography of the scientists Manipur were working at America, UK, France, and everywhere. So I'm presenting to Madam for and if anyone wish to buy, it is available outside. Yes.
Let us proceed for the refreshment.
Please.